Greetings, statistics scholars, and welcome to this video on section 6.4, dealing with inference involving differences in population means. Let's begin this video with a research question. Does the breed of a cat affect its litter size? Suppose that over the course of a decade, visitors to a website dedicated to cats were asked to report the litter size when their cats gave birth, as well as the breed of the mother cat. And suppose that through looking at those records, a simple random sample of 40 Siamese cat births was recorded from those data files, and a random sample of 45 Persian cat births was also taken from the same records. And they were studied to look at average litter size. Suppose we desire, based off of those sample findings, to make a 95% confidence interval for the difference in population means for mu1 minus mu2, where we'll let mu1 be the average number of kittens in a litter for a Siamese mother, and mu2 will be the average number of kittens in a litter for a Persian cat mother. Those are unknown population parameters, and we'd like to form a confidence interval for the difference in those two values. Well, to do that, we must, of course, take some data. And we had indicated before that there had been 40 Siamese cat litters that were studied, taken as a sample from the website data files. And suppose that it's discovered that among those N1 equal to 40 Siamese cat litters, that there is a sample mean of 4 kittens per litter, with a sample standard deviation of S1 equal to 0.75 kittens. And suppose that among the N2 equal to 45 Persian cat litters that were sampled, that for the Persians, the average number of kittens per litter was X2 bar equal to 2.8 kittens per litter, with a sample standard deviation of 0.58 kittens. So now we have some data from our samples that we can use as a basis to build our confidence interval for the difference in the unknown population means. We want to build that 95% confidence interval. And of course, that means starting with a statistic and then building out from a margin of error to create our limits. Well, we'll estimate the difference in those parameters using the difference in our two sample means. Our statistic estimate would be X1 bar minus X2 bar, the difference in the Siamese cat sample mean and the Persian cat sample mean. 4 minus 2.8 gives a difference of 1.2 kittens per litter. In our sample, the Siamese mothers had, on average, 1.2 more kittens per litter than the Persians did. That's our statistic value. And our confidence interval will have that value, the difference in sample means, 1.2, right at the center of the interval. But to finish creating the interval, we of course must find the margin of error and add and subtract that from our statistic. Well, what is the margin of error for this interval? Let's take a look. Now, you may recall that when we were working with a single population mean in section 6.2, we estimated the standard error for the sample means using the formula that standard error was a sample standard deviation S divided by the square root of the sample size N. And that was the formula that we used when we had a single population mean. But here we have two populations with samples being taken from both of them. When working with samples from two independent populations, we're going to see that we have a similar formula, but now that we have a sum of fractions underneath our square root sign. We're going to have the square root of S1 squared divided by N1 plus S2 squared divided by N2. And here we're using the subscript notation so that S1 is the standard deviation, the sample standard deviation from the first sample, and N1 is the sample size for our first sample. Likewise, S2 and N2 are the sample standard deviation and the sample size from the second sample. You'll notice there that the overall appearance of the formula not only bears some similarity to the formula for one population mean, but also is somewhat similar to our formula for standard error for the difference in population proportions, in that once again, we have the square root of a sum of two fractions, each of which has the sample sizes in their denominators. So you'll notice some similarities here, both to our formula from section 6.3 and also certainly similarities to our formula from section 6.2. Let's use that formula now to compute out the standard error for this particular scenario. In this case, recall that there was a sample standard deviation of 0.75 kittens from the first sample and a sample size of 40 births and litters. And in the second sample, we had 0.58 kittens as the sample standard deviation with 45 litters in the second sample. So by substituting in those values of S1 and N1 and S2 and N2, we find out that our standard error here must be the square root of about 0.02154, or approximately 0.146. That's our standard error, a measure of how spread out we think the differences in the sample means will be for samples of size 40 and 45. Now, we want to use that standard error, as we always do, to compute our margin of error. And just as when we found margin of error for a confidence interval for a single mean, we're again going to use a t-star value, a special t value, to help find the margin of error from the standard error. Specifically, we'll use the formula that margin of error equals t star times SE, where t star is the critical value chosen from a t-distribution that gives us the confidence level that we want. Now, you may recall, this is precisely the same formula that we used back in section 6.2 when computing margin of error when working with a single population mean. But now we're going to use it for working with differences in means. To find that special t-star value, we'll use the t-distribution in StatKey or some other technology. It's important that we use the correct number of degrees of freedom for our t-distribution. For problems involving differences in means, such as the ones that we're looking at here, the number of degrees of freedom will be the smaller of N1 minus 1 and N2 minus 2. In other words, we're going to take a look at the numbers that are one less than our two sample sizes, and we're going to choose the smaller of the two of them. In this problem, there were 40 Siamese litters and 45 Persian litters. Well, 40 minus 1 is 39, and 45 minus 1 is 44. So between 39 and 44, the smaller of those two numbers is 39. So we're going to use a t-distribution with 39 degrees of freedom, since that is the smaller of the numbers that we get when we subtract 1 from each of our two sample sizes. Let's take a look at what StatKey reports. Here's a distribution with 39 degrees of freedom, our t-distribution. We indicate that we're interested in a two-tail situation, and we set the proportion or area in the middle between the two tails to be the confidence level we desire. We set it to be 95% here. As soon as we've taken our t-distribution and set the middle proportion appropriately to our confidence level, we then can read off our T-star value. It's going to be that critical cutoff value shown at the bottom at the edge of the tails. And we see that T-star here equals 2.023. That will be our special critical T-star value that will be used in computing the margin of error, 2.023. So now we're ready. We can finish our computation of the size of the margin of error and obtain our confidence interval for the difference in population means. We already knew that 1.2 was the statistic that was in the center of our interval. That was the difference in our sample means. But now we're equipped to find our margin of error. Margin of error is T star, which was 2.023, times the standard error, which was found to be 0.1468. Multiplying those two together, we get about 0.297, just about 3/10 of a kitten. We're going to add and subtract that margin of error from our statistic to find our limits. When we subtract 0.297 from 1.2, we get 0.903, just a little bit above 9/10 of a kitten. And when we add 0.297 to 1.2 for the upper limit, we get 1.497, just a little shy of 1.5 kittens. So now we have our limits, 0.903 kittens and 1.497 kittens as our lower and upper limits. So what do we conclude in the end? In the end, we conclude that we're 95% confident that the difference in the average number of kittens per litter between Siamese and Persian kittens is somewhere between 0.903 and 1.497. Just about the difference, somewhere between about 9/10 of a kitten and 1.5 kittens difference between these two breeds of cats. So I hope that you found this video instructive on the idea of creating confidence intervals when working with differences in population means.